So we're now going to combine a lot of the information that we've gathered so far and talk about atomic physics. So in atomic physics, as you can see from the name, we're going to focus on atoms. We're going to look at different models of the atom, and we're going to spend a lot of time focusing on the hydrogen atom. So let's go ahead and get started and look at early models of the atom. Um, so what is the idea behind even thinking of the atom? So that's been a very long quest. And originally the atom was thought to be indivisible. So that's a word that comes from the ancient Greek, indivisible. So the idea was to look for the most fundamental piece of what makes what we see around us. And so, as we know, it's not actually a fundamental particle because it's made up of smaller structures. And in fact, in 1897, Thomson discovered the electron, which we know is much smaller than the atom. And we know that there's a bunch more particles that are smaller than the atom. And we also know that we have particles at the center in the nucleus, which will be the topic of our last chapter of the semester on nuclear physics. So the atoms were known to be electrically neutral. And so the idea is, so if you think about something that would be that would have some electrons there, but that would be electrically neutral, would be that you could have this sort of plum pudding model that you see here. And so you'd have this, all the electrons, again, that are smaller structures than the atom itself, in this massive positive charge, making the whole thing overall neutral. So there were some experiments that were run to confirm this idea. And one was looking at how alpha particles, so alpha particles is something that we'll talk about a lot more later on also. So they're helium nuclei. And so alpha particles were scattered from gold foil. And what was found was that most of these alpha particles pass through the foil. And so if you think about that, if they were easily going through, it kind of made it seem like, you know, you had this sort of structure that was more like Swiss cheese, where, or at least where there was a lot of empty space, right? So for the alpha particles to be able to just go through. And many more large angle scatters were found than expected. And so if you think about how those particles would be scattered, if you think of having the positive charge all over, you'd get more diffusion, but with large angle scatters, essentially that pointed to the fact that the positive charge were actually not all over the volume, but concentrated in a smaller volume, which we know now is the nucleus. Okay. And so, and again, you know, you go in with a model and you try different experiments, and in some ways, sometimes if you're lucky, you end up getting something that's different from what you expected, and that's how you can make new discoveries. So now we're moving away from this plum pudding where we have, this massive positive charge with a bunch of electrons within, and the scattering of alpha particles on gold folds tells us, okay, no, that doesn't work. There's actually a lot more empty space, and our positive charge is actually concentrated in a smaller volume. So then that led to a new model, and that new model looked more like a solar system. So you can think about the planets orbiting around the sun, and it was kind of the same idea where you'd have the nucleus at the center, which is positively charged, and the electrons orbiting around this, again, a lot more concentrated nucleus that is positively charged. So at this point, I want to pause too, because this is still, for a lot of people, kind of the idea of what an atom would look like. And what we're going to see in the rest of this chapter is that it's actually a bit different than that. So even though, and you still see that on shirts and whatnot, that's kind of the idea of the atom. There are some things that are still wrong with it. And so if we had orbiting electrons that are shown in that the way that they are in this picture, that means that they would be accelerating. If we have electrons that are accelerating, they would be radiating. And the frequency of radiation emitted by a continuously radiating electron would have a continuous spectrum. So it would be continuously accelerating and radiating, and you'd have this continuous spectrum, which is not what is observed. Instead, what you see is individual frequencies. And again, that doesn't fit with that picture. And in fact, that's something that we can see when we look at the spectrum of various atoms. And what we're going to do now is look at one specific spectrum. We're going to look at the hydrogen atom and see that we're not going to see a continuous spectrum the way that this model would, describe any given atom, but specifically in this case, hydrogen. But instead, what we're going to see is that we have some lines. So you can see when we say about, so what I was saying about individual frequencies, you can see it here. So we have a spectrum which doesn't have, which is not continuous. Instead, we have these very definite lines that are happening, as you can see, at very precise wavelengths or frequencies. And so here, what you can do is essentially, it's kind of like a light bulb, but typically it's designed in a little bit of a different way, but you would just fill it with whatever gas you're trying to study. So in this case, we could fill it up with hydrogen. And so we have a high voltage difference that is between, as you can see here, the top and the bottom part of this device here. And what we're going to see is that, so due to this high voltage difference, we're going to have an electric field. And what we see is that essentially we're going to have an emission of light from, so you can see some radiation essentially from that. So it's going to essentially glow, and we can, so what we can see, so if you the same way that you look at a rainbow, right, and you can separate the colors, we can see, okay, so we can see the light that is emitted by this hydrogen lamp essentially. We put that through diffraction grating to separate all the frequencies, and this is what we find for hydrogen. What is very interesting is that any given type of atom, so you could repeat that for helium or any other element, and it would have its own signature spectrum. So that is very interesting. But first of all, you can see that those are lines. So we only have specific frequencies that are available. So that is not explained by the model that we just looked at. And also you'll have, like usually you have a dominant frequency, a couple of ones that give you kind of the overall color of your element. So for hydrogen, you can actually use that to analyze the night sky and kind of tell what elements are present where. So in this nebula that is looking reddish, essentially, we know that there's hydrogen there that's responsible for that color. So that's very cool because that means that you can analyze the light that is coming from various sources, and you can see what would be responsible. So any given atom is going to have their different signature, all right? What is also interesting, so you can see that we have these two pictures. Here we have emission lines, so that's the light that is emitted by our atom, and you can see it's happening at very defined frequencies. And if we have white light that is passing through, what is interesting is that what we have is an absorption. We see absorption lines in the sense of, you can see that now we have the whole spectrum of colors that is being that's shining on our element, and that element is going to absorb only those same frequencies that it was able to emit. So you can see that we have exactly the opposite here, where you can see that the lines that were absorbed are the ones that were emitted here, okay? And so what we're gonna do in the next video is try to figure out, okay, so how do we tell which frequencies we're going to have for the hydrogen atom, and how does that fit in a new model of the atom?